A very good morning to all of you. What a fine day, is it not? So, what else would be better occasion rather than this time to kickstart the second series of events Kubernetes Day Sri Lanka Day 2. So, with that, let me warmly welcome you all. And without wasting any further time, let's jump into the very first session we shall plan for the day. But before you do so, let me give you a quick reminder. Stay tuned, stay till the end because we have a set of sags waiting for you, and they are for grabs for anyone out there who is ready to go for them. So, let me introduce you to the very first speaker for the day. Say hi to Harish Nataraj, and he'll be speaking to us about auto open API generation. So, if I'm to give you a quick background of him, Harish has extensive experience in APIs, microservices, and API security. And he's also the co founder of Levo.ai, which is an API security and observability solution. So, Mr. Harish, the stream is yours.
Thank you so much, Akalanka. Very nice to be on this show. Really appreciate you inviting us.
So,
Um, can people see my screen?
yeah.
Okay, great. Today we're going to have a discussion on API observability, concepts around API observability, and also specifically around API security. And along with that, we're going to talk about auto generation of OpenAPI using eBPF. So what we're seeing today is a rapid transformation of architecture where monoliths or SOA-based architectures rapidly transforming into microservice architecture with distributed systems. And that is being accelerated by the adoption of Kubernetes. So Kubernetes and microservices kind of go hand in hand, and which in turn is leading to what we call as massive amount of API proliferation. There is a massive amount of APIs that are public, private, and that number is growing so fast that one of our customers, mentioned that APIs are growing like mushrooms. He said it in a jokingly way, which in turn is leading to APIs being the de facto attack vector. And so, in terms of security, people always talk about attack vectors, and so the main objective of this slide is to emphasize the point that APIs are the front door to your applications and your data, and they are becoming the de facto attack surface. Next, we're going to actually look at some attack patterns that are pronounced in API-based architectures, especially microservices. The very first attack pattern is something we call as horizontal authorization abuse. Now, this pattern has happened at many big enterprises, including Uber, which grabbed headline news. And this incident is actually from this example is actually from one of the incidents from Uber. So Uber has this notion of ride receipts. You can go back and look at what rides you had over a period of time, and these receipts are encoded with some sort of an ID. So you can each receipt has an ID internally, and each receipt actually belongs to a specific user. And if you're using a mobile, in this case, let's say Troy is a user and he wants to look at his ride receipts from yesterday or day before, what his mobile is doing underneath the covers is simply making a REST API call saying, hey, get receipts with a specific ID number 101. And the backend service routed via the API gateway returns the actual contents of the receipt. And the mobile renders the receipt. And the receipt has sensitive information like from address, to address, credit card numbers, and things like that. So in this case, during the actual attack, Troy, it's not the actual name of the attacker, but Troy is a clever programmer. He was just curious to see whether we can bypass the mobile altogether and use a tool like Postman. So what he did was he took his authentication token from his mobile, put that in Postman, and said, hey, gee, I wonder if I can get receipts for other persons. And so what he did was he made a receipt for receipt number 103. In this case, receipt number 103 actually belongs to Scott. And he was super surprised to find that the backend service routed via the API gateway was readily returning information about Scott's ride, his from address and to address and credit card numbers and so on and so forth. And this is a serious violation of customer privacy. And Troy also realized that not only he was able to get Scott's receipt, he was able to see Kathy's receipt, and he was able to see thousands of other people's receipts going back to several years. And essentially what this is a failure of granular authorization at a microservice level, in this case, the receipt service level. Even though somebody was authenticated, the backend service, the specific service, wasn't actually enforcing granular authorization. And if you just do a simple Google on HackerOne, or just do a Google, this attack pattern is an authorization abuse pattern. It's called IDOR, Insecure Direct Object Reference. And HackerOne calls this a massive rising trend of problems with APIs. So the next pattern that we see is called vertical authorization abuse. In this case, you have multiple roles or OAuth scopes. And roles and scopes are nothing but a certain set of entitlements or privileges. With a specific role, you get access to certain set of information. So in this case, Joe belongs to the manager role, and the manager role has access to the total revenue GraphQL object and the customer revenue GraphQL object. And you see Jan and Tim have a completely different role. In this case, it's called the employee role, and the employee role only has access to the customer revenue object. Now, when attackers or pen testers look at a scenario like this, when there's multiple roles or scopes, what they will typically do is to try to say, hey, can I take a lesser role in the sense that something that has lesser amount of privileges, and try to escalate privileges for that. And which means they will try to see if Jan and Tim can actually access something like total revenue objects. And if that does, that is a privilege escalation and a serious issue where you're getting access to data that you're not supposed to get. So these types of attacks, the previous attack which I showed you is the horizontal authorization abuse, and the current attack, the vertical authorization abuse. These types of attacks are specific to every business. There is no single common authorization logic across businesses. So that's why we call these business logic attacks. And these are becoming very, very prevalent with the APIs, because with distributed systems and distributed teams, implementing granular authorization authentication across so many different APIs, so many different services, so many different time zones, and across so many different releases, and trying to keep them consistent is a massive challenge. And really what enterprises really need to solve this problem is what we call as API observability. And really preventing this type of abuse patterns means granular observability of API behavior. And I'm going to explain what we really mean by granular observability. So in terms of access patterns, you have users like Joe, Jan, and Tim. And then you have roles, like I showed you earlier, the manager role and employee role. Now, the roles can also be scopes in some cases, like OAuth scopes. But for this purpose, let's just like keep it simple and call it roles. And then you have specific JSON objects that people have access to. And those JSON objects are actually accessed via certain API endpoints. And ultimately, observability is about understanding the relationship between users and roles, and what objects that users have access to, and ultimately via what API endpoints. So essentially, what we're saying is you need access visibility at a very, very granular JSON object level via the API endpoints. That's what we mean by API observability from a security perspective. Now, there are techniques of getting observability for APIs, and I'm going to examine these existing techniques or conventional techniques. So this slide, essentially the outcome of the slide is you want to get to observability of saying, hey, which users under what roles are accessing what APIs and what JSON objects. But the very first technique that's been used for a long time is what we call as network packet capture or network traffic mirroring. So like in AWS API Gateway, you have traffic mirroring where you can see all the API calls, and based on the API calls, you can piece together this information. But the problem with this type of observability technique is it needs to have access to every single network packet. And if there's any TLS and most microservice architectures are embracing TLS these days. Capturing network packets makes you totally blind for TLS. So essentially, this technique suffers from a lack of visibility because of TLS. And the other drawback is it's highly CPU intensive because like you have to take every single network packet and stitch together the full API payload or API stream from network packets. This is a pretty dated technique that is not applicable in modern architectures. But there's newer techniques, and people familiar with the microservices and service meshes and things like that. They know of the sidecar pattern, sidecars that are enabled by things like Envoy and Linkerd and a few other techniques. And what the sidecar does is it's a full reverse proxy, and it's actually both a forward proxy and a reverse proxy. And it can actually give you access to API traffic. You can make copies of the API traffic and then analyze the API traffic. But unfortunately, while the service mesh or sidecars have a lot of value in terms of capturing the full payload and analyzing the payload, it requires a lot of application changes. You have to inject sidecars, or you have to change your application configuration to include a sidecar. There are also drawbacks of increased latency, and potentially when you're debugging problems, you always have to isolate, hey, is it a sidecar problem or is it an application container problem? And those types of things, which generally make troubleshooting a nightmare. A third technique that people are using is something related with open telemetry or tracing. Companies like Dynatrace, Datadog, New Relic, AppDynamics kind of sort of popularized these open tracing technique. And open telemetry is a new standard. But again, with open telemetry, you have to collect the full baggage, the response and request of the API payload. And it has the same type of issues, like, it requires application changes because you have to embed some sort of agents, you have to make SDK changes. It increases the latency because you have to capture the full API request and response, and could potentially lead to instability in applications and things like that because you're messing around with app payloads and things like that. So essentially, the available techniques are too intrusive, cause a lot of friction between security teams, developers, and DevOps. And that's where a technology called eBPF, or Extended Berkeley Packet Filters, that has been around for the last 10 years, but is being massively being adopted now, makes a massive difference. eBPF essentially makes the whole observability of APIs super frictionless. And we're going to examine how that works. So in this diagram, what I'm showing you is a Kubernetes cluster, and that Kubernetes could be running in Amazon as EKS or GKE or AKS, or it could be somebody's on-premises data center. And you have lots of microservices workloads in different namespaces. And within that environment, what we do is we introduce a lightweight, non-inline eBPF sensor. What do we mean by non-inline? It's not a sidecar. It is not a SDK or in-application agent. It is completely passive. It is not associated with the workloads. It's typically installed using a daemon set that runs at the host level. And it does not require you to instrument every single workload, application workload. It's completely done at the host level. So this basically eliminates all the friction of the previous types of instrumentation techniques, where you don't have to go to every single development team and say, hey, include this agent or include this SDK. You install at the host, and none of the other teams are impacted because this is completely passive. It's completely non-inline. It's running at the host level and will not increase latency or will not lead to crashes or instability of the application workloads. And what does the eBPF sensor do? The eBPF sensor is capturing the full request and response payloads of every single API call. And these API calls could be REST API calls, could be gRPC, could be GraphQL, or could be async API. It doesn't matter, because pretty much all these calls happen over HTTP, and so all HTTP traffic is fair game, including Kafka. If you look at Kafka as an API, capturing Kafka traffic is also fair game. Now, I think in some of the previous sessions in this forum, I heard about data privacy being a very, very important concern. And whenever you capture API traffic and you build an observability platform, the whole idea of the observability platform is to give you observability of auto discover your APIs, and give you OpenAPI schema, auto discovered OpenAPI schema for all those APIs. But if this observability platform is running in somebody else's cloud, like a vendor's cloud, you don't really want to send your API data out of your data center, out of your VPC into somebody else's cloud. That is a privacy and a compliance issue, because APIs have all kinds of sensitive data, and you don't want to send all that information to somebody else, which is a compliance nightmare. And that's where, from an architectural perspective, privacy, privacy preserving technology is a very, very important consideration. And that's where the satellite plays a very, very important role, which is running inside the customer VPC or the premises. And this next slide is going to explain how the satellite, makes sure that none of the customer data is actually going into the vendor's observability platform or cloud. And all that is going into the vendor's cloud is purely the API metadata, nothing about the real data itself, but API metadata. Ultimately, in the observability platform, what you want is auto discoverability of your APIs and auto documentation of your APIs in OpenAPI format, along with a few other use cases, which we're going to get into a little bit later. So this next slide is going to explain how the satellite works. So, like I said, data privacy and compliance is a very, very, very big architectural concern. So the satellite, which is running within the customer VPC or the premises, accepts data from the sensor. So the print on this slide is a little small. Hopefully people can see it. But what we've done is there's a post API call that's being captured by the eBPF sensor and is being sent to the satellite. And as you can see, it has all kinds of sensitive information like usernames and email addresses and credit card numbers. And if that information goes to the vendor cloud, like I said earlier, it's a compliance and a privacy nightmare. So that's where the satellite comes in. And the satellite guarantees that none of that data will ever go into the vendor's observability platform or vendor cloud. What goes into the vendor cloud is purely data inferences. And what do we mean by data inferences? So on the left-hand side, you can see an ID with a value 72565. And what is the satellite doing? It's looking at every one of these keys and values, and it's deducing the data types. So essentially, we're deducing OpenAPI data types. And what actually goes into the vendor cloud is purely the API metadata or data inferences. Essentially, the data OpenAPI data types like, hey, this is a string, this is an ID, this is an email, this is some sort of a PII, and the ranges of the strings. What is the string length, and what is the range of integers, and so on and so forth. So ultimately, when we send all this data to the cloud is stitching together, auto-discovering every single API endpoint, and showing you full OpenAPI specifications with the data types. And the next set of slides is actually going to explain all this stuff. So just to reemphasize, any sort of API observability solution has to be data privacy centric. It should not consume the data directly. It should only consume data types or data inferences. Never send the actual data to the vendor's cloud. So let's actually look at what are the various benefits of API observability. So the very first benefit, like we said, is hey, we need to understand what all APIs they have. Because when we talk to most enterprises, they all know they have hundreds and hundreds of APIs, but there is no consistent way of knowing what is the actual format of the APIs, what is the JSON schema of the APIs, what kind of sensitive data exists in those APIs, and who is actually consuming these APIs? Who are the users? Where is that API being, which services are consuming the users? Which external users are consuming those APIs? So fundamental problem with any sort of initiative, be it a security initiative or sort of like what do you call a reliability initiative, asset visibility of, hey, what APIs exist, who are using them, is a fundamental ask. And that's where the top benefit is auto discovering all your API environments, be it REST APIs, be it GraphQL, be it gRPC, or be it async API, to have a comprehensive real-time catalog where every single API is discovered and kept fresh. Unlike developer documentation that is like a point in time, in the sense that you build an API, you document it, and you publish it in some sort of API catalog. Oftentimes there's drift where you make changes to the actual code, but you forget to update the documentation. So as most documentation initiatives, it's always a challenge to keep them fresh. So that's where when auto APIs are auto discovered, they're always fresh, in the sense that there's never a stale situation of like, hey, oh, the documentation actually doesn't match the API, because we're discovering API documentation or API structure from live traffic, and this can be in staging environments or in production environments. It doesn't matter. And apart from just knowing what APIs you have, you also need to know the JSON structure of those APIs, because today's language of APIs is JSON and JSON schema. And so not only do we have the auto discovery of the APIs, we auto generate fully compliant OpenAPI specifications for these things. So this is an example of a fully generated OpenAPI schema, and it's being shown on Swagger UI, but it is completely discovered from a real live traffic by reverse engineering the specification. And if you notice very closely, there is also these extensions. OpenAPI supports extensions, and within these extensions, we are auto-discovering roles or scopes. So if you're using OAuth scopes or role labels as part of your JWT tokens, JWT, JSON Web Tokens, we can decode them, and as part of the API documentation, show you what scopes and roles are being used. I'm going to kind of zoom in here. So that is what I'm talking about as the extensions for roles. And zooming in further, you can see that role user, role mechanic, and role admin, in this specific API, there are 3 roles that are being auto-discovered. And that is being done by decoding JSON Web Tokens from the real live traffic that is fed to the discovery platform. So once you have set of APIs, you understand what is the structure of the APIs. You also understand what's which roles are actually accessing the APIs. That is the foundation, like I said, for many initiatives, including reliability initiatives. Not only for reliability. I mean, if you have a large team and you want to understand dependencies, who is calling my APIs. I mean, internal teams may be calling APIs, and you want to understand which internal teams are calling you. Or if you depend on other teams providing APIs, you want to understand, hey, which other teams that you're depending on APIs. You can get all that information here. So moving on to the next use case, apart from the basic foundation of visibility, let's some analytics use cases here. Here we're talking about analytics for least privilege. APIs are a conduit for data. Ultimately, API itself is not interesting. What is interesting is like, hey, what is the data that is being queried and what is being returned by the API? So ultimately, data is the most important thing, and authorized access to data is the most important thing from a security perspective. And there's a principle in security called least privilege, in the sense that you only want to provide users as much permissions as they really need. You don't want to over permission them. And that's where with the APIs, when you have thousands of them, you can get what you call sort of drift in terms of permissions. And over time, many people are going to have more permissions than they really need. And you need to actually audit and make sure that you're not over provisioning users or roles or scopes with API access. And that's where we can provide analytics on API usage because we're collecting API data. We're collecting the full response and request payload. So what we can do is we can cluster API behavior, like API access patterns. And clustering means it's like clustering algorithms saying, hey, what is the cohort of behavior? Certain types of users have the same type of access pattern. So every one of these circles denotes a unique set of access patterns or common set of access patterns. And if I were to drill into one of the circles and say, hey, what denotes that access pattern, you can expand and actually get a full detail of, hey, what set of APIs are being accessed and how frequently are these APIs being accessed. So you can ask questions like, hey, I see that the patch user ID salary is only being used 1% of the time, and for a cohort of 1,000 people. And do I really need to provide all these 1,000 people access to the patch, or should I segment that further, and segment and create another cohort, another role that only provides access to the patch API, so that many people who don't really need access to patch should not be given the patch access. So this is one of the fundamental things of security, least privilege. I believe there was a session about Kubernetes APIs earlier in the early sessions, and they talked about least privilege and Kubernetes RBAC. This is not about Kubernetes APIs. This is about actual application APIs. But the same concept applies to any sort of API. Role-based access control, attribute-based access control, and least privilege. Be it Kubernetes APIs or application APIs, it's all the same. But there's lots of solutions today, including Kube itself, kind of gives you solutions at the Kube API level to say who has access to what APIs. But if you have your own APIs, it's really hard to ask those questions. And that's why you need solutions, API observability solutions that focus on those types of APIs. Now, the next benefit is centered around service-to-service communications. So typically, in a microservices, you have like hundreds of services talking to each other. In a completely flat network, any service should be able to talk to any other service. But the fundamental problem, again, applies here. The least privilege principle, again, applies here. You do not want to give every service the capability to talk to every other service. There is no legitimate business requirement for any service to talk to any other service. And if you do that, what happens is, like, in security, people talk about, data breaches and lateral movement, where attacker, breaks into one of the services and then starts to laterally move from one service to another service, and from that service to jump to another service, and basically compromising each service until they get to the gold mine of interesting data. And lateral movement is a very common attacker technique, and people talk about segmentation strategies to lock down this type of lateral movement. And in order to segment, people earlier on in static environments were using IP addresses. And this is a Kubernetes forum, and people would be very, very familiar that Kubernetes workloads are extremely ephemeral, containers are short-lived, and this whole notion of IP doesn't really make any sense. Really, IPs are short-lived, unlike traditional systems where an IP used to live for years, servers used to live for years. Here, services are very short-lived, and so an IP gets recycled. So doing what you call segmentation, that a service on this IP address can only talk to another service on this IP address, that is a very old concept. What today you need to do segmentation based on application and API constructs. You really want to say, hey, service A can talk to service B, but on specific API routes. And what do we talk about? What do we mean by API routes? It's basically the URI subpath, like the slash users or slash policy or slash payments, those types of URI paths of the API. And you say, hey, service A is only allowed to talk to service B on these specific routes. And you definitely need analytics, because without analytics, it's very hard to lock it down, because in brownfield environments, people do not put these policies in place. And typically policies, what do you call segmentation policies, being retrofit. And when you have to retrofit these policies, you need to have visibility on which services are talking to which other services on what specific API routes. And once you have the visibility, you can ask the question, hey, are these legitimate business requirements? And if they are, you can put policy to say, hey, okay, service A is allowed to talk to service B on these specific API routes. So those are the benefits of high-level benefits of API observability. And next, since we've talked enough about what is API observability, what are the use cases, what are the benefits, what are some of the techniques that we're used currently, and what are the drawbacks, and why does eBPF actually make a big difference here? I'm going to spend some time actually talking about eBPF itself, and what is the mechanics of eBPF. So this is a primer, and it's kind of high level, but there's a Q&A section in the end, and we can drill down into further details if required. But essentially, let's actually examine a Linux host or a virtual machine and see why eBPF makes tracing of APIs frictionless compared to other systems. So this is a Linux host where you have the standard user space, and then you also have the underlying Linux kernel that comes with every single host. And we're all familiar, we write applications, we write microservices, and these are called workloads or application workloads. They tend to run, they could be containers, but they all tend to run in the user space of Linux. And those application workloads use things like system calls, like in order to send traffic to some other service, like HTTP call, an API call happens over HTTP, and that HTTP call goes over TCP, and all TCP calls get sent over system calls, like send, receive, send to, and those types of things. And so every application workload has to use the underlying kernel's system calls. Application workloads also use encryption functions. So typically, in order to send data to another service and make sure that nobody else can read it, you have to TLS encrypt it. And TLS encryption has user space libraries like SSL read and SSL write. Your OpenSSL library provides these functions so that before any sort of data is actually transmitted over the network, it is transmitted in an encrypted format. And so those application workloads also access those higher layer functions to encrypt the data. And in order to actually get API visibility, what that means is you need to actually tap into these function calls and copy the data in a passive manner. So a sidecar, is actually inline. It's a full proxy. It's sitting inline with your application workload. So any data that's sent is actually being processed by the sidecar proxy. The proxy can make a copy and then retransmit the entire data outward, or any incoming data actually traverses the proxy. But in this case, there is no proxy, and we want to copy the data. And so that's where we need to actually, attach or probe, or what put like in simple terms, like developer debugger terms, put breakpoints at these function calls so you can inspect them and copy the data. And that's what eBPF provides. eBPF is sort of like a very, very, very lightweight debugger. Its magic is about attaching to these function calls, allowing you to inspect those function calls and copy data from these function calls. eBPF has a in-kernel virtual machine that allows you to program the kernel to copy data or inspect things. And you typically have a user space sensor program that sends program instructions to the virtual machine saying, hey, do these types of things. And essentially, what are those programmatic instructions? It's telling the eBPF virtual machine, the user space sensor is telling the underlying virtual machine to put probes or breakpoints at strategic system calls like send, receive from, send to, and those types of things. And also put what you call user space probes at strategic locations like SSL read and SSL write, where encryption happens. So unlike other techniques like network packet capture, where you can copy packets but be completely oblivious to the encrypted information, eBPF can actually give you visibility into pre-encrypted traffic, because we are putting the probes at a much higher level. And what do these probes do? what are the K probes? K probe means kernel probe, and U probe means user space probe. And what are they actually doing? What they do is they allow you to copy data, inspect data, and copy actual API full request and response payload, and transfer that to your sensor using something called maps or perf maps, performance maps or perf maps. So all the API data is captured, copied in a passive way without impacting latency, without impacting the actual application logic or the resiliency of the application. And that data is being copied and sent to the eBPF sensor. So at a high level, that's how eBPF works. And the next set of slides is going to talk about, give you an example of how this actually works in terms of eBPF. So here I'm going to talk about the anatomy of how eBPF will trace an API call. You have a simple Python server that is basically using an OpenAPI specification. It's taking an API request and returning an API response. And you have an API client. It could be Postman, it could be a browser, whatever it is, and the client makes a simple API call. In this case, the API is like demo hello world. That's the API route. And when the server receives this request, there is a system call called receive from that first gets triggered. And this is a TCP system call or a BSD socket system call that gets triggered. And like I mentioned in the previous slide, we have programmed eBPF to actually put breakpoints or inspection points or probes into these strategic system calls. And so what happens is our first probe, eBPF program, will attach to the receive from call and copy the incoming data from that client. And once that copies, it'll move the data that has been collected to a perf map or a BPF map that I talked about. And that BPF map is where your user space application can or sensor can actually get access to that data. So the second thing that happens is like when your receive from system call exits, that is what is telling BPF that, hey, stop copying data. And so we both not only instrument the beginning of the system call, we also instrument the end of the system call using probes, and we will know when to start data capture and when to stop data capture. Then finally, that data is actually going into your Python server. The Python server processes that data and then sends a response back. And when it sends a response back, it is going to use a system called send to. It could use many other variations of send to. It could use send, it could send to, it could be send v or write v, those types of things. But essentially, the same thing happens. When the send system call happens, we have programmed eBPF to instrument that call. So at the very beginning of the system call, we start collecting data or capturing or copying data. And at the end of the data transfer, once we copy the data, we push it to the map. So the sensor actually has a copy of the data. And then when the send to system call ends, we know exactly when to stop capturing the data. And then when the full send to system call completes, the final response to the client is going to go out. And so that's essentially the anatomy of how throughout the what do you call it, the anatomy of how eBPF captures a request coming from the client and a response going back from the server. And so this happens for trillions and trillions of API calls, and all that's being sent to the satellite, and the satellite's actually going to capture that data, sanitize the data, not actually take the data, but do data inferences, send it to the platform which is running on the cloud, the observability platform. And the observability platform gives you OpenAPI specifications and the analytic workloads or analytic use cases I talked about earlier. So that's kind of like how the whole mechanism works and the whole value proposition of what we call as API observability. This speech or discussion was centered around security use cases, but there's also many use cases got to do with DevOps, reliability, and debuggability and things like that. So if you're having errors, if you're having latency, and all these things, eBPF is a very powerful technique to capture metrics around number of errors or 99 percentile latency on these API calls. That's a different subject. Totally possible using the same technique. Fundamentally, the concept remains the same. The security application is a little different. The monitoring for DevOps and reliability applications is a little different. But the packet capture, sorry, not packet capture, the instrumentation techniques and the overall concepts remain the same. That's all I had in terms of content. I have a bunch of time for questions, but I do see a bunch of comments come in terms of questions. I will try to answer each one in sequence. I think the very first question is, how is the eBPF sensor going to fulfill GDPR compliance? That is a fantastic question. I'm going to switch to the slide here on observability and answer the question. So fundamentally, what is happening is with GDPR, there are two types of concerns. One is if you are sending your data to somebody else's cloud, potentially you are leaking your customer information to somebody else's cloud, and that is a big no-no, because your data should not go to somebody else's cloud, even though the other vendor may claim they have SOC 2 compliance or ISO compliance, and it's that still it's a big issue of sending your data to their cloud. And that's where the whole satellite comes into play. And what the satellite guarantees is any data collected from the sensor is fully scrubbed, and all the data going into the vendor's cloud or the observability platform in the cloud in the SaaS does not actually have any customer data. All it has is data inferences or data types. So from an audit, a GDPR or PCI or HIPAA audit perspective, none of your data is going into the observability platform vendor's cloud. So that is clean, and you can actually prove to the auditor by putting a tap on the satellite and showing that no real data is going into the vendor's cloud. So that's one aspect. But from GDPR, there's also another aspect. So you personally have to prove, as an organization, you have to prove to an auditor that you have done what is known as a data privacy impact analysis. And what do we mean by data privacy impact analysis? You have to show, because you have hundreds of microservices, you need to know exactly where personal PII, personally identifiable information or personally sensitive information, is actually flowing within the organization. Where is it being stored? Who is consuming it, and things like that. And that's where a solution like this can really help, because it knows which services exist, which APIs are consuming what type of sensitive information. It can actually draw you a graph of, hey, where is credit card information flowing, or where is email addresses flowing, where is it being stored, and things like that. So just by putting one single sensor in your Kubernetes environment, you can immediately, within a matter of seconds, produce a GDPR privacy impact report that you can give to your auditor and say, hey, here are the services that consume this type of sensitive information, and these are the types of people that are consuming it. And if you find discrepancies, if you find a service that is not supposed to have GDPR data consume it, then you can take corrective action. So that should answer the question around how is eBPF sensor fulfilling GDPR compliance. The next question is, which are the efficient methods of avoiding capturing the payload of microservices API call when using external APIs? I'm trying to understand the intent of the question here. Which are the efficient methods of avoiding capturing the payload of Microservices API call when using external APIs? I am not sure if this question is from Mr. Chandri Sadeep. Not sure if I fully understand that. So if you don't mind clarifying that, I really appreciate it. Until then, I will move to other questions if there are.
Hi, Harish.
Hi,
Hey.
Akalanka. Yeah, so,
So,
doesn't
yeah.
look like there's any other questions. So I wasn't sure if I really understood that question. So if there's a
Yeah, so in the meantime, maybe like till you clarify the question, maybe you could fire some of our questions, the questions, a few questions of our own
yes, yes,
towards the
please,
audience.
absolutely, absolutely, yeah. Yeah.
Yeah, sure. So you can go ahead.
Oh, sorry, you're asking me to
Yeah, yeah, yeah.
ask questions to the audience?
Yeah, around maybe two, three questions.
Okay, yeah. So, question about like how many people are this is a Kubernetes conference, so everyone should be doing multiple services, microservices, APIs. Probably in that context, how many people are using REST APIs? How many people are using gRPC? How many people are using GraphQL? Or what percentage of people are using these three technologies?
I, for one, I have only experience working with REST APIs.
Right.
How about the audience? Okay, I see we have another question upcoming.
Uh, if you're using a different log analytics like elk, how do we ship required log to them? So I think maybe the question is like, if I understand that right, that he's asking if how can I ship the entire API request and response payload to the elk solution? So we have a tap in the satellite. This is the satellite, and we have a tap in the satellite where you can the satellite exports data in open telemetry format or open OTel format. You can consume that, and then you can export it directly to your elk provider. Cool. Yeah. So, question about different types of open API formats or like API formats. Who's using what? I know Akalanka mentioned REST APIs. Anybody else wanting to chime in terms of what they use? gRPC, GraphQL, etc.
I guess we have no more questions, right? So in that case, thank you, Harish, and thank you
Yeah.
for joining with us. And wait, we have another question. So before we conclude, let's have another look at it as well.
I guess like it was somebody answering, mostly REST, but they use some sort of gRPC and a little bit of GraphQL. So
I see. Okay,
great.
great.
Thank you so much, Akalanka. Really enjoyed the session, and happy rest of the day.
Same to you.
All right.
So looking forward to meet you in another next session maybe. So
Absolutely.
for that, let's call it quits.
Thank you so much.